Hello everyone! In this video we will continue to examine topic 12.1, quantum and nuclear physics, and in particular we will begin to discuss the uncertainty principle. Alright, so the uncertainty principle, or the Heisenberg uncertainty principle, is an important consequence of the rest of the postulates of quantum mechanics. So it's not an extra thing. And the fundamental derivation of the uncertainty principle comes out of the mathematics of the wave function itself. But we're going to start by simply describing a little bit of how it works. So the first thing I want you to consider is the wave function of a free particle. Okay, it looks like this. We've called this a wave packet. And the first thing is to recognize that the wave packet indicates for a free particle indicates that the location of the particle itself is not completely unbound, but is described by the wave function. And so we can, with some probability, find that particle here. This means the uncertainty of the location of the particle can be described by the region sort of where the wave function itself is. Okay, so the particle is with some probability at each of these particular points and is with almost certain probability in this region. Okay, and so we can describe the uncertainty of the exact location of the particle with delta x. It's important to note that that uncertainty is not like the measurement uncertainty that we've been using throughout this course. That's an epistemic uncertainty. That's about whether we know it's somewhere or not. In this case, this is much deeper. This is an ontological uncertainty, or an uncertainty in where the particle is whatsoever. There's no truth of the matter as to where the particle is, if this is the wave function that corresponds to the particle. But we can constrain that uncertainty to within the bounds of the wave function itself. So without measuring, its location is uncertain, and that uncertainty in the position is delta x as shown right here. But we can also ask a similar question with respect to the speed, the velocity, or the momentum. So how fast is it moving? And without measuring, its velocity or momentum is also uncertain. And take a look at this. We know that through the Heisenberg uncertainty principle, through the de Broglie hypothesis, lambda equals h over p. This means that the wavelength of the wave function is inversely proportional to the momentum, and therefore the momentum and the wavelength carry sort of the same information. And notice that in this wave packet here, there is a wavelength of sorts between sort of different peaks. But as sort of a hand-wavy approximation here, if you take a look at this wave packet, you can see, well, here's sort of a wavelength, and here's sort of a wavelength, and here's sort of a wavelength. And as it turns out, as a matter of empirical fact, wave functions that operate like this don't have sort of a single well-defined wavelength. They have sort of a range of wavelengths. And we can understand that uncertainty in the wavelength as being related to the fundamental uncertainty in the momentum. So the uncertainty in the wavelength is related to delta p, or p max minus p min over 2. Really just p max minus p min, I guess. And in any case, with some more advanced mathematics that sort of come out of the nature of the wave function, it's sort of related to its waviness. It can be shown that the uncertainty in the position and the uncertainty in the momentum multiplied together have a lower bound. That is, that they are at least as big as h over 4 pi. Okay, and this is the Heisenberg uncertainty principle. It is one of the most important sort of results of quantum mechanics, and is also, I will say, partially responsible for some of the sort of worst pop-sci versions of quantum mechanics. Okay, this is a very specific thing. It comes out of the mathematics of the wave function, and it says that the uncertainty in the position and the uncertainty momentum are related and form a through multiplication, a lower bound. Okay, and we'll talk about the consequences of that. Quick note, everyone else in the world is going to write it like this. They're going to use sigma for the uncertainty in both cases, okay, lowercase sigma, and they're going to write the right-hand side as h bar over 2 pi. H bar shows up all over quantum mechanics. It's just Planck's constant with a bar through the top, and it just means h over 2 pi. So everyone else in the world is going to write it like this. But this is the version we'll use, and you should be familiar with.